We're given a function y equals f of x, defined and continuous and differentiable on some domain, maybe the entire real number line, maybe some finite interval. We're interested in knowing, at some number, call it a, what is the equation of the tangent line then? So this curve is the graph of y equals f of x, and this line is the graph of some linear function. Y equals maybe L of x because it's linear. But it's supposed to be the tangent line at this point. This point is the point a comma f of a. And if it's a nice function, the slope there is f prime of a. A is some fixed but unspecified number. What is the equation of L of x? That's our goal. L of x is a function whose graph is the tangent line at this point. It's also called a linear approximation to f near that point. Sometimes also called the local linearization of f near that point. It approximates f well when x is close to a. F of x is approximately equal to L of x when x is close to a. But what is the formula for L of x? This should seem familiar. It's f of a plus f prime of a times x minus a. I just used it in that implicit differentiation example with a equal to 3. What was x? X was equal to 3.01. These equations, these approximations are exactly the same, with a equal to 3 and x equal to 3.01. And you were doing this kind of stuff back in chapter 2. We're just being a little bit more formal about it right now. In section 3.9, homework will be due a week from now. You have problems like, oh, here's f of x. F of x is square root of 1 plus x. Square root of 1 plus x. And a is 0. Find L of x. Find the linear approximation to the graph of this near this point. Just use this formula. That's all you have to do. F of x is square root of 1 plus x. That's the same as x, 1 plus x to the 1/2 power. So I need the derivative. I get 1/2 1 plus x to the negative 1/2 power. By the chain rule, I also multiply by 1, the derivative of 1 plus x, but that doesn't change anything, pun intended. So you don't have to write times 1. A is 0. I need to evaluate f of 0 and f prime of 0. F of 0 is square root of 1 plus 0 is square root of 1 is 1. And f prime of 0 is 1/2 1 plus 0 to the negative 1/2. 1/2 times 1 to the negative 1/2. But 1 to any power is 1. We get 1/2. Therefore, the original function f of x, square root of 1 plus x, is approximately L of x. Using this formula, L of x equals f of 0 is 1, f prime of 0 is 1/2, a is 0. This simplifies to 1/2 x plus 1. That linear function, slope of 1/2 and a y-intercept of 1, approximates the graph of f of x really well near a equals 0. Graphically, if you graph both of these on your calculator, you'd see something like this. There's f of x, and L of x would look like this. And here's an example of an application of it. Square root of 1.1, for example, is f of 0.1. Think about that. That's approximately L of 0.1. Plug 0.1 into that function, you'll get 1/2 times 0.1 is 0.05 plus 1, 1.05 is an example application. Is that right? Is square root of 1.1 close to 1.05? Yes, it is. Not exactly, but close. To end class today, I want to help you a little bit on your project. We'll do more linear approximations and more project stuff next Monday. Probably do another implicit differentiation example as well to make sure you get that. Linear approximation, what I was just talking about, can help derive the formula for Newton's method that you end up using in the project with the Newton plot code. What is a typical application of Newton's method? A typical application of Newton's method is it's a method to find, for example, square roots. Now you might say, hey, we just found a square root in this problem here. And that's true, we did. And we used a linear approximation. But Newton's method is a different way of using linear approximations to get approximations to roots. And in the big scheme of things, Newton's method works better. You've got some function, f of x. That's a nice continuous and differentiable function. And maybe its graph crosses the x-axis somewhere and you'd like to estimate where it crosses. Let's put this in the context of an application. Let's say our goal, this is an example goal, not the only goal, is to estimate the square root of, I don't know, 12 with Newton's method. The way to do that is to say to yourself, what's a simple function that square root of 12 is a root of, a 0? The simplest function I can think of that doesn't involve irrational numbers in it is x squared minus 12. That's a function that has an x-intercept at the square root of 12. Right? If you plug in square root of 12 in place of x, square root of 12 squared is 12. 12 minus 12 is 0. Newton's method says that to estimate this number, which is an irrational number, let's see what it is on a calculator. Square root of 12 is about 3.464101615, blah, blah, blah. I'd like to approximate this number, maybe even without a calculator. You come up with a guess first. Square root of 12 is certainly between 3 and 4. Maybe you guess the simple number 4 to begin with. Call that x sub 0. That's like your seed, as in the project. Is it right? No, it does not equal square root of 12. But it's not super far away from it. The method goes up to the curve, finds the tangent line at this point, and figures out its x-intercept, and that is called x1. But it's a recursive method, iteration. Do it again. Take that point, go up to the curve, find the tangent line, and find its x-intercept, and I already can't draw it very well because it's so close to the root. x2 is even closer to that root square root of 12. But this begs a question. How do you find x1 and x2? Here I'm drawing them, but what's a formula for them? It's a recursive formula. X sub n plus 1, the next value of x, is the previous value of x minus a certain fraction. That fraction is f of the previous value of x divided by f prime of the previous value of x. By the way, this graph up here is an example of something you would get if you use the Newton plot code in the project. And this ultimately is what you are iterating. This function, you could give this another name. You could call this g of xn. And you could use nest list, for example, to iterate that. But the Newton plot code does it for you and makes a picture for you in the project. So let's try to apply this here. I've got f of x. I need f prime of x. That's easy. That's just 2x. So for this example, this becomes xn minus f of xn. I need to go to the formula for f and write that up here with an xn in place of the x, divided by f prime of xn. That'll be 2xn. And this is the function I need to iterate. So, for example, if x sub 0, the seed, is 4, this implies that x1, the next value of x, is x0 minus x0 squared minus 12 over 2x0. Since x0 is 4, that's 4 minus the fractions 4 squared minus 12 over 2 times 4. Simplify. That's 4 minus 4 squared 16 minus 12 is 4. 2 times 4 is 8. 3.5 is what I get for the next value of x. Is 3.5 close to the square root of 12? Well, it's certainly closer than 4 is. Do it again using 3.5 now. x2 will be x1 minus the fraction x1 squared minus 12 over 2 times x1. In other words, it's 3.5 minus the fraction 3.5 squared minus 12 over 2 times 3.5. That numerator, 3.5 squared minus 12 is 0.25. And the denominator here, 2 times 3.5 is 7. Actually, this is a 1/28. We had a 1/28 elsewhere today. 0.25 divided by 7 is 1/28, which is this. 3.5 minus that number is 3.4642857. That is getting really close to square root of 12. Compare. There's x2, there's the square root of 12 to that many decimal places. They're getting really close together. If you did one more step, it would be really close. What's a quick way to do this on a calculator? Same kind of way you did on the first 4 exercises of the project. Use the previous answer button. Here's my initial guess, x0. However, my function that I iterate here is kind of complicated. It's this. Use a and s in place of xn. So I get previous answer minus, I better use parentheses here because I'm dividing two things here. I'm subtracting the whole thing. Previous answer squared minus 12 and parenthesis divided by 2 times previous answer. Did I need a star in there? I forgot a star. Let's see if it works. Yep, 3.5. The next one should be this 3.4642857 when I hit enter again. Yes, it is. If I hit enter a couple more times, I bet if I now also hit square root of 12, we may be correct to that many decimal places. Already, yes. After just ultimately 4 iterations. That's pretty impressive. Newton's method converges very rapidly to the right answer. And if you end up, if you're like a computer science major, or if you have to do scientific computing, Newton's method is something that's used quite a bit to estimate roots of functions. Sometimes you just have to do it this way because there's just no simpler way to do it. It's very efficient. In your project, when you do the Newton's method part, just like with the other parts, you should expect strange things to happen. It's supposed to happen. Help you realize as a lesson for the project that even in relatively simple situations, strange things can happen. So you need to beware. Don't be afraid to experiment with the project. Try some code, maybe it doesn't give you the graph you want. Try a different window. Try a different seed. For example, to estimate repelling fixed points, that's pretty necessary. There's that one problem where you're trying to estimate two fixed points. One's very easy because it converges to it, it's attracting. There's another one up here that's repelling. You're not going to find it unless you do lots of experimentation. Okay? As a word of advice.